Now in this last problem, this is an example of a pretty tricky combustion analysis problem. And the reason it's tricky is because we actually have three separate experiments that are taking place here. We have experiment number 1, where we're starting with 2.52 grams of the compound, and we are getting 4.36 grams of CO2 from the combustion analysis and 0.892 grams of water from the combustion analysis. Then we have experiment number 2, where the key thing here is that experiment 2 starts with a different amount of the original compound. It starts with 4.14 grams of the original compound. And this time we're just getting from this particular analysis, we're getting SO3. So not CO2 or water, but a different compound entirely. And then same thing's the case for the third experiment. Oops. We're starting again with a different amount of the compound. And we're producing just one thing here again. So this is 2.8 grams now of HNO3. So why this problem is so tricky is because you can't just solve for the mass of carbon and mass of hydrogen in this first experiment, and then the mass of sulfur in the second experiment and the mass of nitrogen in the third experiment, and then combine them all together, because they're not coming from the same original compound mass, right? The amount of compound that we're coming from is different, so we can't compare across these experiments directly. So this causes a problem, especially because if we notice up top here, the compound that we're dealing with has carbon, hydrogen, nitrogen, oxygen, and sulfur in it. And from these experiments, we don't have any information right now about the oxygen. And we've seen before that, if there's one element we don't have information about, we can usually get that information from having all the values for these other elements. But we need to do that properly. We can't compare things that don't make sense to compare. And in this situation, that means we can't just use the masses that we're given. So what are we left with as a tactic here? Well, for this type of problem, I'm going to introduce you guys to a slightly different way of solving these combustion analysis problems that will also work for simpler versions of these problems. And it involves solving for the mass percent of each of these elements in the original compound, and then using the approach we saw previously of using the mass percents of each element to get the empirical formula, where if you remember, that means we usually assume 100 grams of the compound, and by doing that, then we do have values for each element that are going to tie back to the same amount of the compound. But in order to get to that point, we have to first figure out what is the mass percent of each of these elements in the original compound. So I've cleaned this up a little bit, and we're gonna see something really familiar, hopefully by now, here, which is taking this mass of the CO2 from the first experiment and the mass of the water from the first experiment, and using the mass percent of carbon in CO2, so set up as an expression here, because I'm not gonna bother solving for the mass percent, I'm just using it as a conversion factor. And I'm using that to get the number of grams of carbon in this original 2.52 grams of the compound. Same thing with the hydrogen. Again, remember that for the mass percent expression, you have to multiply the hydrogen by 2 because there's 2 hydrogens in water. That's a really crucial step there, or you'll get the wrong value here for the amount of hydrogen. Now you may remember that once we have these amounts of carbon and hydrogen in the original compound, we can easily solve for the mass percent in that original compound by just comparing the mass of carbon to the total mass of the compound that it comes from. And same thing for the hydrogen, the mass of the hydrogen compared to the total mass of the compound that it's coming from. So notice here, this is another mass percent that we're setting up now, but it's for the compound, it's not for the CO2 or for the water. And so our component here is still carbon on top, but our total on the bottom is for the original compound. And this is where it's really crucial to make sure you're using the correct experiment starting mass of the compound. So for experiment 1, that starting mass was 2.52 grams. So I've set these mass percentages up, I've multiplied by 100, and I'm getting my mass percent now for my carbon and my mass percent for my hydrogen. And remember, these mass percents, those are going to be the percent in any amount of this compound that we have. So it's the mass percent in 2.52 grams of the compound. It's the mass percent in 100 grams of the compound. So that mass percent is such a useful value because it can be referenced back to any amount of the compound, which is what's going to allow us to tie all of these things together from these separate experiments and actually compare the individual elements. So for experiment 2 and experiment 3, I'm doing the exact same thing, except I'm using these other things that were formed as products. So we had this SO3, the sulfur trioxide, 2.6 grams. And again, I'm using the mass percent of sulfur in the sulfur trioxide. So you need the molar mass of sulfur trioxide on the bottom. You need the molar mass of one sulfur on the top, since there's only one sulfur in the sulfur trioxide. And that's going to get us the mass of sulfur in the original compound in experiment 2. Same thing with experiment 3, except this is now HNO3. And again, we're interested in the nitrogen that's coming from this compound, because all of the nitrogen that shows up in this product came from the original compound. So one nitrogen in this molecule means just the molar mass of nitrogen on the top, and then the bottom here is the molar mass of this HNO3. And so that gets us the mass of nitrogen that came from the original compound in experiment 3. So again, remember these masses right here for sulfur and nitrogen, we can't compare them to the masses for carbon and hydrogen from experiment 1 because they're not coming from the same starting amount of the compound. And as a reminder of that, note here, I've gone ahead and listed what that starting amount of compound was for each of these experiments. So we can see here, again, it was 2.52 for experiment 1, it's 4.14 grams for experiment 2, and it's 5.66 grams for experiment 3. So we've definitely got different amounts of our starting compound. But again, the mass percent is a way to express these amounts of these elements in a way that we can compare them all to each other. So when I want to get the mass percent now of sulfur, I'm taking the amount of sulfur that came from this original compound, and I'm dividing it by the total amount of that compound that was used in experiment 2, and multiplying by 100% to get my now percentage of the sulfur. And then I'm doing the same thing for the nitrogen. I'm taking the amount of nitrogen that came from the original compound in experiment 3, and I'm dividing it by that mass of the original compound that this experiment started with, times 100% to get the mass percent of nitrogen. Now, these mass percents that I've got here now for carbon, hydrogen, sulfur, and nitrogen, those can all be compared to each other, and they can be used to solve for oxygen, right? Because we've still got this one element left in this compound that we haven't solved any information about because we weren't given any information about oxygen. Now, those of you that are looking at this and going, well, can't you get some information about oxygen from the CO2 and water, or from the SO3, or from the HNO3, because they all contain oxygen? And I'll remind you that, again, most of these processes, these reactions that are taking place when we do these analyses of these experiments, involve introducing oxygen. So if you're introducing oxygen and it's not coming from the original compound itself alone, then you can't really figure out which oxygens in each of these compounds came from the compound and which oxygens came from the added oxygen. So oxygen is almost always going to be the element that you save till the end to solve for based off the other information that you have. Now, the way that's going to work is we're going to just subtract each one of these percentages that we found from 100, because if there's only one element left, then whatever's remaining after we subtract out all these other percentages should be equal to oxygen. Because remember, the mass percent of each one of the elements in the compound should add up to 100. So if we've got everything but one element, then we can subtract all those values from 100 to get what oxygen's percentage is. And so that is as simple as just kind of punching in all this long string of subtractions into your calculator, and you get this percent for oxygen. So now that we have all the mass percents, this is the point where we're now going to assume 100 grams of the compound, just so that we have an amount of compound to start to work from that is going to be the same for all of these elements. And so this is basically what you do. It's the same sequence of steps now from here on out. of what you do when you're given a problem where you're given the percent composition of all the elements and asked to solve for the empirical formula. That's the step we're at right now, because we've solved for all the mass percents, the percent composition essentially of this compound. So we're going to move forward with the same process we would use, starting with those percents and trying to figure out the empirical formula. And for that, remember, assuming this 100 grams of compound makes it so that we have values that are just coming from the percents themselves. So we can assume 100 grams so that each one of those percentages we had becomes the number of grams of element that we're dealing with. Because if 47.214% of 100 grams is going to be due to carbon, then that's going to be 47.2147 grams of carbon, right? So the reason for 100 grams is just to make this easy so that we can take our percentage values and use them as the masses of each of these elements. And so if you remember, at this point, now we have masses of the elements that all come from the same amount of compound. So we're just converting them into moles, because in order to find the empirical formula, we have to compare the moles of each element. So for carbon, we're just dividing by the molar mass of carbon to get how many moles of carbon there are. For hydrogen, we're doing the same thing. We're dividing by the molar mass of one hydrogen to get how many moles of hydrogen there are. And we just go down through the list and do this for all of the elements. And then when we go to compare them, remember, you want to identify the element that has the smallest number of moles, because we're going to basically divide each of these other elements by that smallest amount and see if we get a whole number ratio. So over on this side now, I've gone through and I've divided each one of the elements by the moles of sulfur, because that was my smallest value. And also note that, your moles of nitrogen and your moles of sulfur here are pretty much exactly the same. So we're expecting to get about 1 for the ratio between them. And so we notice that right here, that dividing these two, we get the value 1.0084. And we also notice that we have sort of a similar condition here with oxygen. It may at first look like this is a very different number of moles, but when you divide them, you actually get 1.00930. So notice here, these numbers that I'm getting for all these ratios aren't exactly a whole number, but they're really close. So it is fine in this case to round to the nearest whole number value and use that as your final sort of basis for how many of each of these elements we should have in the empirical formula. So just note that, right? I'm rounding each one of these to a number. Now, typically, in order to feel comfortable rounding, you should have something that's pretty close like this. So there should at least be a 0 next to the decimal place so that you can round down to 5. Or if this was like 4.9 or 4.99 or 0.96 or something like that, if you have a 0.9 value, then you can round up to 5. So that is usually fine. Be careful though, because I've already done an example where we didn't get a whole number when we did the ratio, but we got like a 0.5 value. If you get 5.5 here, then you need to multiply that by 2 to get up to a whole number. And that would mean everything would get multiplied by 2 to get what that whole number is going to be. If you get a 0.25 or a 0.2499 or 0.2501, or sorry, 0.2501, something that's close to 0.25. Let's recognize that 0.25 can be made into a whole number by multiplying by 4. And so if one thing needs to be multiplied by 4, everything would need to be multiplied by 4. The last one to watch out for is 0.33. So if you get something that's like exactly a third, right, 0.33, then you'd be multiplying by 3 to get that to a whole number, and everything would get multiplied by 3. So watch out for those sorts of cutoffs. Most of the time, these numbers will be very close to a whole number, but if it's in that 0.25, 0.5, or 0.33 range, then that is a case where you can't round. You want to actually multiply by a whole number to get the value into a whole number, and then multiply everything else as well by that whole number. And if you want to see an example of how one of those situations is handled, number 10 on the worksheet deals with one of those situations where you don't get exactly a whole number from this ratio and you have to multiply. But for this one, we're good because these are all close to whole numbers. So we just use these values as our subscripts. And remember that since we divided by sulfur, that means that this is all per 1 mole of sulfur. So sulfur also gets a 1 subscript, or basically no subscript, in this empirical formula.